Hey everybody, welcome to Lecture 16, Moisture, Clouds, and Precipitation. We are going to be covering a lot of information here, mostly about cloud formation, but to do that, we need to start with matter and heat. As we know, there are three states of matter. You have liquid, solid, and gas. To change their state, heat either has to be absorbed or released by an object. So for a solid to turn into a liquid or a liquid to turn into a gas, heat is needed. But in order for it to go from a gas to a liquid or a liquid to a solid, the opposite happens. Heat is released. In order for heat to be absorbed and for a degree of, let's say, 1 gram of water to be raised, you have something called a calorie. This is the heat necessary to raise specifically 1 gram of water 1 degree Celsius. Latent heat is stored or hidden heat. It's the heat that's already in an object that when it changes its state, it gets released. This is the heat exchange between water and its surrounding, which is very important for atmospheric processes. Let's take melting. Melting is changing from a solid to a liquid, and in order to do so, you need 80 calories per gram. Freezing is when your liquid becomes a solid. In this case, you have the release of latent heat. Yes, the freezing process releases heat. And evaporation, when liquid becomes a gas, you have 600 calories per gram added, and then you have the latent heat of vaporization. Condensation is water vapor changing to a liquid. Again, heat is released. And then we have sublimation. Sublimation is when a solid changes directly to a gas, and you need about 680 calories per gram added. And then deposition is when your water vapor becomes gas to solid, which is what we see at the bottom here. If you look directly below me, you're going to see ice on a window. That is deposition. It's when it gets so cold so fast that instead of dew forming, it just freezes. Anyway, again, heat gets released in this process. All in all, melting and evaporation are the cooling process for the atmosphere as they gain energy and drop in temperature, but condensation and freezing are the warming aspects of the atmosphere, as this is a loss of energy, the release of latent heat. And this is what we call the water thing of energy transfer in our atmosphere. Now let's talk about water in the air, or humidity, which if you're from the East Coast, you are very, 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 very familiar with humidity. On the West Coast, not so much, and that has to do with the currents that we learned about in the oceans lectures. So saturated air. What is saturated air? This is air where you have water in it and it can't take in any more. It can't hold any more water at all. Think of a sponge. When it's a little wet, it can hold more water, but when you've dunked it in the water and let it absorb as much as it can, all that water that's excess just drips right off. And we're going to talk again also about vapor pressure, how we measure humidity by looking at water vapor content. So let's say you divide it by the mixing ratio. In that case, you will have relative humidity. And when your relative humidity is 100%, you have a saturated amount of air. Remember, humidity, the amount of water vapor in the air. Saturated air is when your air is filled to capacity. You cannot take any more liquid, any more water into the air itself. The atmosphere is full. Okay. Capacity is going to be temperature dependent. Warm air has a greater capacity for more water than cold air. So for example, if you had a saturated parcel of air and it dropped in temperature, that's how you get rain. That's why right before a thunderstorm, the temperature drops. Vapor pressure is the pressure added to the air with humidity, meaning that the pressure of air goes up the more saturated it is. And we measure humidity in two ways. You have the mixing ratio and you have relative humidity. Mixing ratio is the mass of water in a unit of air compared to the remaining mass of dry air. And this is always measured in grams per kilogram. So the big thing you need to remember is mixing ratio, grams per kilogram, measures the mass of water vapor. Relative humidity is the ratio of the air's actual water vapor content compared to the amount of water vapor required to reach the saturation point at a specific temperature and pressure. This gets turned into a percentage. So remember, relative humidity, percentage, actual water vapor content. Mixing ratio, mass of water vapor, grams per kilogram. And so let's look at the Erlenmeyer flasks. Here you have an Erlenmeyer flask that has air in it that's at 25 degrees Celsius. You have 1 kilogram of air for all three of these. The saturation mixing ratio at 25 degrees Celsius is 20 grams. We only have 10 grams of water vapor, which means that if we have 10 grams of water vapor in the air and our maximum is 10 over 20, we're at 50% humidity. Now let's drop the temperature to 15 degrees Celsius. Same thing, except now at 15 degrees Celsius, the mixing ratio is 10 grams, meaning the maximum amount of water vapor content you can have, its saturation point, is 10 grams. We have reached 10 grams. Therefore, the relative humidity is 100%. Let's drop it again. Now we're going to drop it to 5 degrees Celsius. Still 1 kilogram of air. Now the saturation mixing ratio at 0 degrees is 5 grams. The water vapor content, the maximum amount of water vapor we can have in the air is 5 grams. We still have 10 grams of water in here. So what you'll see at the bottom is 5 grams of water as a liquid is on the bottom of the Erlenmeyer flask. Because we've dropped the temperature and the saturation point is now 5 grams of water, that other 5 grams of water needed to literally fall out of the air, forming water at the bottom. That's how rain works. Now we have 5 grams remaining, meaning we are at 100% humidity. Now let's take a look at some really cool graphs here where we're going to see almost exactly a mirror image of each other. Up at the top, we have temperature, and at the bottom, we have relative humidity. You can see they're actual direct mirrors. Let's say we have 5 grams of water. If you look at the lowest temperature, we have the highest relative humidity. That's because, like we saw in the previous slide right here, the lower the temperature here, the less water vapor can be contained in the atmosphere itself. So if we're over here and we're saying, oh, hey, look, lowest temperature is right here, highest relative humidity, we only have 5 grams. That means at this temperature, we have a good portion of what's able to be met by the atmosphere, what's able to be absorbed, has been absorbed. Maybe the maximum is 7 grams of water, and we've hit 5, so we're at 70%. But over here, we have a higher temperature, a much higher temperature in Celsius. And so what happens here is we are now at our lowest relative humidity. The reason behind this is that the higher the temperature goes, again, the more water can be taken into the atmosphere because your saturation point rises. How do we measure moisture? We use something called a hygrometer. A hygrometer can be broken into 2 types. You have the psychrometer and the electric hygrometer. A psychrometer, most commonly is the sling psychrometer, is made up of 2 thermometers, which we can see right here. One thermometer is going to have this little nifty sock on it, and you're going to dip both sides into water. Your dry side is going to dry out fairly quickly, or you could just wipe it off with a napkin, up to you. And basically, you swing it in the air like this for about a minute or 2. And so what you have to do from this is you're trying to take energy from the thermometer to dry or evaporate the water that's on the sock. And so we spin it in order to simulate wind. If the 2 thermometers, after spinning it, are close in temperature, it means the moisture in the air. If the wet sock is cooler, then you have drier air, and then there's a lot of energy being used for evaporation. Basically, it means you have a lower amount of humidity. But if the air is really saturated, both of the thermometers will actually read the same temperature, which is pretty cool. But the greater the difference in those 2 thermometers, the lower the relative humidity is. The closer they are, the higher relative humidity is. The electric hygrometer is much easier. You just kind of like turn the thing on and stick it up in the air and it says, oh, hey, here's your relative humidity. Much easier, much faster. Over here, what we have is a map that is made up of humidity. And what we can see on this side is, one, we have this arrow drawn up here. That is the direction that the current goes along the east coast. So you see it's going to bring up warm water, which is going to make it a lot more humid on the east coast. We have a similar current system in the Gulf, so all in here is also going to be quite humid. But on the western portion of the United States, we have this north to south current, which is bringing our cold water, which means it's going to be a lot drier. You're not going to have as much humidity. Why do we have such a little amount of humidity in the Midwest? That's actually because of the mountains. Mountains actually block humid air, and so what that means is that you're actually going to have rainfall on one side and then dry air on the other, and that's part of why you get these huge dry portions of the United States. Now we're going to move on to clouds. The cloud equation is super duper important. It's the way that clouds form. You have to have water vapor, first of all, which is a limited resource because it depends on the temperature, how much water vapor you have. And water vapor doesn't just condense into clouds. It doesn't just go, ta-da! it needs something in order to form, which is known as a nucleus. And the nucleus is made up of dust, and that includes dust from like your skin, pollen, dust from lawnmower clippings, dirt being kicked up into the air, sand particles. All those form nuclei, where water vapor then condenses around it, and that's how clouds form. Next, you need a condensation process. There are several, and we're going to learn about them. And this leads to cloud formation, and because we're having condensation, latent heat release, which means we're heating the atmosphere by forming clouds. The first cloud formation process is going to be adiabatic cooling. And in this one, the first thing we're going to look at is this little icon over here, TD. TD is dew point. It is separate from temperature. It is the temperature at which water will condensate. And usually that's cooler, so which is why in the morning you tend to wake up and there's like water everywhere on your car after a cooler night versus a really hot day. That's condensation on stuff. That happens regularly because we have humidity in the air, especially in Florida. And so once you get a drop to a certain degree, just like we saw earlier with the Erlenmeyer flasks, you're going to have water just literally fall out of the sky. And it's going to condense onto things that it can, things that have dust particles on it, and like your car. Dry adiabatic rate is when you have unsaturated parcels of air. The rising air will expand and cool at 1 degree Celsius per 100 meters, and then if it descends, it will compress and warm at 1 degree Celsius per 100 meters, which we can see down here. This is the dry adiabatic rate. Okay. But cloud formation will begin at the condensation level, which we're going to say is about here. At this point, you're going to have reached the dew point. Condensation will begin occurring, and latent heat will be released. And then you get sensible heat, which is released by condensing water, reducing the cooling rate. Basically, meaning that as the water condenses, because it's heating the atmosphere and releasing heat, it's no longer going to cool at 1 degree Celsius per 100 meters. It now will be something more like 0.5 to 0.9 degrees Celsius per 100 meters. And how stable your air is at this point is going to impact atmospheric motions. The atmosphere is naturally going to be unstable. Air always wants to mix or overturn, which is how you form clouds. Overturn is the change from stable air to unstable air, or WC over C to CW. Mixing is when you have warm and cold air mixing together. Generally, this tends to form rain. And when you make a cloud, you need that dew point. You need unstable air in particular. And as the cloud rises, again, it warms the air. And so what you end up having is that the cloud will end up rising pretty high. And that's how you get your higher level atmosphere clouds, is because it's warming the atmosphere so much, it's going to continue to be less dense and so rise. But what about rain? How does rain work with this? You're getting clouds. Clouds means rain, right? Well, it can take a few hours for precipitation to occur after a cloud has formed. And there's actually a few ways that rain ends up forming, and we'll learn about those later. The wet adiabatic rate with cloud formation and condensation level, again, creates this sensible heat. So don't forget about that sensible heat. It's very important. And so you're going to have more likely rain with the wet adiabatic rate than the dry adiabatic rate. But it also depends on what else is happening in the atmosphere, what kind of wind currents are happening, what time of year it is. Is it going to freeze up there, or is it going to stay liquid? All right, so stability is the impact of atmospheric motions. Atmosphere is naturally unstable. In order to make a cloud, you do need to reach the dew point. You need the temperature and the dew point to actually match for condensation to begin. Every 100 meters, there is going to be a drop of 1 degree Celsius, but cloud formation will create heat, meaning they grow as they rise, and they will slow when there is reduced mixing or when it runs out of moisture. With the dry adiabatic rate, which is on the other side here, air is unsaturated, and rising air expands and cools, and descending air compresses and warms. And remember, I said about precipitation, it needs a few hours to form. Now let's go over processes that cause condensation. The first one is cooling. This leads to things like radiation fog and has a drizzle. You have surface cooling, where the ground cools, which leads to stratus clouds, and again, tends to have more drizzle. When you have cooling and lifting happening, such as convective, which is every day, it's diurnal, it's something that happens all the time. That's what leads to our thicker cumulus clouds. And when you have advective, or when you have orographic or mountain lifting, it leads to a mix of clouds, where you'll have some thinner clouds at the bottom and it'll get thicker and thicker as you go up. When you have mechanical or frontal lifting, such as when you get a cold front or a warm front, you're going to have sustained lift, meaning there is no limit to how high it could possibly go. Everything has a cap, but you could get things such as cumulonimbus clouds, where it rises like thousands of meters into the atmosphere. Now let's go over orographic lifting. We mentioned it before. This also leads to things like the rain shadow effect. Okay, orographic lifting is when you have an elevated terrain like a mountain, like we have over here. We have mountains, just like the Rocky Mountains. This is actually where this happens. The Himalayas also are another one. The Cascades, the Rockies, the Himalayas, they all cause this, what we call the rain shadow effect. Basically what happens is humid air goes up, and because as it goes up and up and up, it reaches the dew point and so condenses, forming clouds, and then it rains because it can't go any higher while it's holding all this rain. And then this now dry, warm air will go down the other side, forming the rain shadow effect. And so what this leads to is a very dry area on one side of the mountains, but a very wet, humid, maybe even tropical area, depending on where in the world you are, on the other side. One of the more well-known areas is the Himalayas, where on one side, on India, for example, you have these lush rainforests, but on the other side, you have this huge dry basin, which is where Mongolia is, and a couple other Middle Eastern countries. In the United States, the orographic lifting has led to the creation of the giant redwood forests that we have up in Washington and Oregon. Another one is frontal wedging, where you're going to have this cool air forming essentially a barrier for warm air and shove it up into the air, which is going to cause thunderstorms to form as it creates these huge towering clouds. And fronts like this, these fronts that meet like this, are part of what create the mid-latitude cyclones that we have, which are those huge things that we see on weather maps, where they're like, oh, we have this mid-latitude cyclone forming, where we have this massive low pressure system that's just going to bring a ton of rain down the west coast or down the east coast. This is how thunderstorms are made, as well as tornadoes. Frontal wedging, again, we have it written down here for you guys to see. Cool air becomes a barrier, makes it stop. So the warm air, because it forms this wedge, the warm air that gets shoved up like this. And as they mix, they're going to meet the dew point, and they're going to just create these huge cumulonimbus clouds, and it's super duper cool. Another one is convergence. Convergence is when you have air flowing together and rising. This is very characteristic of what we see on the coast of Florida, where we get those huge thunderstorms coming in off the coast in the evening. It's because the wind directions actually shift. So instead of air going this way off the coast, we have air coming in from the ocean, and that air is very, very warm, and it's meeting much cooler air on the coast, causing it to rise and essentially creating these thunderstorms that happen every evening. Another one is going to be convective lifting, which we see up here. Convective lifting is very localized. It's very central to one spot. You're going to have very localized heating. So basically you have one spot that's getting more heat than other areas. It's got moisture. That moisture is going to be evaporated. It's going to rise, reach the condensation level, and form a cloud over that one spot. It creates these warmer pockets that are more buoyant. And these warmer pockets are actually called thermals, where you have this one area of land getting heated, which has whatever moisture getting evaporated, going up, developing clouds, fueled convection, and then you have sinking air going down the outside. The movement of warm air upwards that will have a higher humidity will cool, forming clouds. Now let's talk about air stability. We've mentioned the fact that you have stable and unstable air in the atmosphere, and the atmosphere always wants to be unstable versus stable. It doesn't like being stable. And so this is where we get the stability of air determining cloud development and its type, and then the intensity of precipitation that happens afterwards. This also influences how the temperature above a parcel of air will change with height and environmental lapse rate. The environmental lapse rate is how temperature changes, okay? So that's all you need to remember that. How does temperature change? That is the environmental lapse rate. Stable air will have no adiabatic cooling. This leads to widespread clouds with little vertical thickness, more like stratus clouds. Precipitation will be light to moderate, whereas if you have absolute stability, you're going to have an environmental lapse rate that is less than the wet adiabatic rate. Absolute instability, on the other hand, is when air acts like a hot air balloon. Rising air is going to be warmer than the surrounding area and so less dense, which means it will rise until it reaches an altitude with the same temperature as the cloud itself. Here it will undergo adiabatic cooling, forming clouds. The environmental lapse rate will be at a greater rate than the dry adiabatic rate, so you'll often get these towering cumulus or cumulonimbus clouds from this. And then we have unstable air. Unstable air means your air is warmer than the surrounding air. So whatever this pocket of air is that's going up is warmer than what's around it. And so it wants to continue to rise rather than sink. So it will continue to do so until it reaches that stable area where it is now at the same temperature and what's around it, which will then be its dew point. Conditional instability, though, is when the atmosphere is stable for an unsaturated parcel of air, but not for a saturated parcel. This leads to super variable cloud formation. This is when you're going to see things like stratus, stratocumulus clouds, cumulostratus, nimbostratus, a whole bunch of different types of clouds forming at once. And here's a visual representation about how air rises and expands. And again, here's an example of absolute stability and how it works, where you're going to have air rising. So let me go ahead and get my pen. You're going to have air rising, and as it cools, you're going to have cloud formation start to happen as it reaches the condensation level. And again, because condensation releases heat, it's going to continue to rise, creating these higher and higher clouds, which is cool. Conditional instability, you're going to have rising until we hit our condensation level, and then it will just grow upwards. Cloud formation. Condensation surfaces on the ground include your grass, a car window. If you're outside and you're sleeping in the open air, you will wake up with dew on you. This is how we get things like dew, fog, clouds. Water vapor requires a condensation surface to form back into a liquid, which is why it can be you. It could be your car. It could be dust, smoke from a fire, ocean salt, pollen. When we have nimbus clouds, for example, Dragon Ball Z, when you call for them, they come down and you get transported to your destination. Or maybe it's the German motorbike, also known as a nimbus. But nimbus clouds are really more like this. It's this beautiful, poofy, cotton ball-y type cloud that we associate with looking at the sky and seeing shapes. Nimbus clouds are major producers of precipitation, and we have all seen them when they're really dark colored, and we call them thunderheads or storm clouds. Nimbus means rainy. But then you have other ones where you have cirrus clouds, which are very high in the atmosphere and they're really thin. Then we have our stratus clouds, which are sheets or layer that cover much of the sky like a blanket. Clouds are really made of millions and millions of minute water droplets, or, depending on where you are, tiny ice crystals. For those of you who have not seen that episode of The Magic School Bus, I encourage you, because you actually get to watch how the clouds form with the frozen parts, where they're actually frozen up in the sky and then they fall and become rain, which is really cool. Clouds are generally classified by their height, not how tall they are, but where they are. Your high clouds are going to be above 6,000 meters. They are going to be cirrus, cirrostratus, and cirrocumulus. Then you're going to get your mid-latitude clouds or your medium clouds. These are going to be 2,000 to 6,000 meters, and this is where you're going to get altostratus and altocumulus. And then we have our low-latitude clouds. These are going to be below 2,000 meters. They are going to be stratus, stratocumulus, and nimbostratus. Remember, nimbus means rainy. Then we have our vertical clouds, the clouds that go through all three of these levels, and that is going to be our cumulonimbus and cumulus clouds. And we'll see that on the next page right here, where we have our high latitude clouds, our middle latitude clouds, our low latitude clouds, and then clouds of vertical development, meaning that they grow in height. They start at the lowest point and grow up to the highest point. And this is why when there's severe thunderstorms around your airport, planes won't take off and they'll try to avoid them. It's because cumulonimbus clouds go so high that it's really hard to actually fly over them, because you actually will get caught in it. So again, here we have cirrus, cirrostratus, which kind of make everything look hazy. cumulonimbus, which are like really tiny cotton balls. Our middles with altostratus, which kind of look a little bit like our regular blanket stratus clouds, but are a little thinner. And our altocumulus, which are like really small cumulus clouds. They look like a whole bunch of little cotton balls being stuck onto a thing, or mini mushrooms. Then we have our nimbostratus, which is going to be our more rainy stratus clouds. They're a little bit higher than our normal stratus clouds, and stratocumulus, which kind of look like bars of puff across the sky. Here are some real pictures of what these higher clouds look like. So we can see cirrus clouds, and cirrocumulus. This is what cirrostratus looks like. If you notice, it really just looks like it's really hazy. That is actually cloud formation. This is how you can actually see some really interesting photos here where you can see it almost like a rainbow in the clouds itself around the sun. You can also get something similar to that at night with the full moon. Then we have our altostratus. We should all recognize this from when we have just those miserable days. And then our altocumulus, where it really just looks like a bunch of cotton balls stuck together in the sky. And then we have our lows. Our lows include nimbostratus, stratus, and then we have our vertical developments, which start at the low point, cumulus and cumulonimbus. Cumulonimbus. Vertical development clouds mean that they start at the lowest point and again form to high altitudes, known as cumulonimbus, which produce a lot of rain and thunderstorms. Now let's talk about fog. Fog is cool. We have fog in Florida. You have fog along the East Coast. Fog happens often on the West Coast, particularly in San Francisco. It's actually quite well known in San Francisco on the Golden Gate Bridge. Fog is a cloud that has its base, its bottom, at or near the ground. This makes an atmospheric hazard because it can block the vision of drivers. This is why we have fog lights on cars, some cars, not all cars. So if you notice you have a set of headlights up here and then below another set of headlights, those are your fog lights. You don't want to turn on your headlights during fog because the light actually bounces back and essentially blinds you, so it's better to keep your lights off. Radiation fog, which is our first form of fog we're going to talk about, radiation fog, is when the Earth's surface cools rapidly. Okay. This means that during cool, clear, calm nights, basically fall, not Florida fall, but regular fall, when normal states have fall, your surface tends to cool almost overnight. Advection fog. Advection fog occurs when warm, moist air moves over a cooler surface. This is what happens in San Francisco. And this occurs a lot in areas close to water, like a beach or a lake. We get advection fog in Florida a lot. And then we have upslope fog. Upslope fog is when you have your humid air moving up the slope like of a mountain, forming adiabatic cooling. This occurs in mountainous regions like the Himalayas, the Rockies. And this also leads to the formation of monsoons, which in such areas affects the rain shadow. And these are all forms of radiation fog, which are all radiation caused fog, where you have radiation cooling or movement of air over a cooler surface. So here's what advection fog looks like over cold water at San Francisco. It's actually really cool to see this rolling in off of the ocean. And you go from being able to see how far away the water is to feeling like you're literally high in the sky and having no sense of how far from the ground you are. It's so neat. This is radiation fog. This is what we're used to, both radiation and advection fog here. It can be a little unnerving, especially at night. If it's in the morning, but you have the sun coming up, the sun will burn away the fog eventually. And so you're going to have more going on where you can see a little bit better, especially as the fog moves away. Now we have evaporation fog. Evaporation fog, we have two types of fog with that. We have steam fog and frontal fog. Steam fog is when you're going to have cool air moving over warm water, and the water appears to steam. Sometimes we can see this early in the morning on cooler days. Like in Florida, when we have our cooler weeks or cooler months where it drops down to the 50s, you can drive past the Hillsborough River and actually see fog coming off of it, and it's really neat. Another one is frontal fog. This forms during frontal wedging, so when a warm air is lifted due to a cold front wedging underneath it. rain evaporates to form fog in this instance, which is pretty neat. Here is steam fog. Again, we'll see this over the Hillsborough River in Florida, sometimes in the morning in fall when we have a particularly cooler evening the night before. And over here we have a really nice fog map. Over here we have advection fog. We can see days with heavy fog, especially in this area of the United States, is going to be somewhere between 40 and 80 or more, and it has to do with the cold current coming down. Where over here we have a warmer current, but because of cooler nights and warmer days, we're going to have more advection or radiation fog in our portion of the United States. And then over here where we have the mountain ranges happening, we're going to have upslope fog, and the same thing will happen over here. We'll have upslope fog. Okay, now we're going to get to the types of precipitation formation. Precipitation formation starts with evaporation, as we know. Remember the cloud equation. You have to have water vapor, and then that water vapor has to condense into clouds, and then in a cloud, water droplets have to form. So yes, I know, you're probably like, but a cloud is all water, right? It's not like in Aladdin where they're whipping around it and it looks soft and you can touch it and essentially eat it like ice cream. No, it is a bunch of water droplets. If you were to fly through a cloud, you would get soaking wet. But these water droplets are all nuclei. They're all centered around dust particles, right? Whether that be smoke, some sort of dust from the ground, very fine particles of ash. Is going to have lots of these nuclei. And these are all going to be less than 20 micrometers, which is about 0.02 millimeters in diameter. These fall incredibly slowly, meaning as long as they stay that size, we're not going to get them, probably ever. Instead, the cloud must grow these water droplets, which means they have to collide. I don't know if you've noticed, but if you've ever shoved two water droplets together on a table, it becomes a bigger water droplet. If you've ever watched rain go down your window, when two raindrops collide, it makes a bigger raindrop. The same thing happens in a cloud. As these little condensation nuclei collide, they're going to make larger and larger and larger cloud droplets until eventually it reaches 2 millimeter, which is the size of a typical raindrop, which here is the size of a condensation nucleus. Here is a typical cloud droplet, a large cloud droplet, the size of a typical human hair, and a raindrop. So the first type of precipitation formation is collision coalescence. This is when you're going to have those rain droplets just combine with each other and hit each other over and over again, basically collide, hence the collision coalescence process. This always happens in warm clouds. It's going to have large hygroscopic condensation nuclei, and large droplets will form. These droplets collide with each other during their descent, making bigger and bigger and bigger ones, and as they get bigger, they fall faster. And this is essentially causing mixing to happen faster, and this is the warm rain process. Okay, this is most common in the tropics. As mixing occurs in the atmosphere, more rain forms. What about up north, where it gets really chilly? They're not going to have this constant mixing and formation of rain droplets. Heck, in some places, rain shouldn't even be happening at all. It's too cold. That's where we get the Bergeron process. This is the second, and it's known as the cold rain process. The temperature of the cloud is instead super cool. And instead of water collecting around these nuclei, you get ice crystals. And these ice crystals collect water vapor, forming large snowflakes. And then they'll fall. And as they fall, depending on the temperature as it goes lower in the atmosphere, it will either melt and become a raindrop or stay and form snow. This is the most efficient process of forming rain because it forms precipitation even when you wouldn't normally have it. Forms of precipitation involve these. There is a lot. You only need a few to remember in your study guide. The first one is rain. We're all familiar with rain. You have to have a droplet of at least 0.5 millimeters in diameter. Next is drizzle. Drizzle has droplets less than 0.5 millimeters in diameter. Mist has the smallest droplets that are able to reach the ground. Snow is made of ice crystals or aggregates of ice crystal. Each snowflake is actually unique. No two snowflakes are the same. Sleet is small particles of ice in winter. It often forms when you have pockets of warmer air overlying cooler air. And so what happens is your snow falls, melts, and then freezes again. And then it leaves layers of ice everywhere, and it's really dangerous. And it looks really pretty, but you don't want to be outside in it. It's not so pretty when it falls after it's pretty. Next is glaze, also known as freezing rain. This is what we call ice storms. Yes, up north, there are these magical things called ice storms. Essentially, rain falls from the sky, and because it's so cold that once it makes contact with stuff, it freezes. And that's where you get stuff like this. This is happening. And you can lose power. You can have this problem where you can't open your doors of your car. Your car is frozen in place. Branches fall because they're too heavy because there's ice. But man, is it beautiful. It is really pretty to see. Next, we have rime. I'll show you rime in a second because rime is really cool. So hail is balls of ice that essentially fall as rain, or little things of ice fall. They get pushed back up into the cloud, where they get bigger and fall and get bigger and fall and get bigger until eventually they're too big for the wind in the cloud to hold up and they fall to the ground. These are commonly what occurred during like really big thunderstorms, especially thunderstorms that lead to tornadoes. Rime is cool. Rime is when you have, it's kind of like dew, but frozen. So we'll go ahead and look at a picture of that in a second. So here's winter precipitation. Here's how it works. Either you have snow forming and then it melts because there you get through a pocket of cold, warm air, and so it becomes rain and never refreezes. If you have snow that melts and then refreezes, you get super cold raindrops or freezing rain. And basically what happens here with these, when you get freezing rain like this, the water itself is super cool, but has not had the agitation it needs to start freezing. And yeah, freezing needs a nucleus too. So as it hits something, it gets the agitation it needs in order to freeze on contact. Snow that kind of melts and then refreezes becomes sleet, which are little ice pellets. And then if there is no warm air at all, you just get consistent snow. No melting occurs. Again, hail is these hard rounded pellets, basically hard concentric shells of ice. And here is a piece of a hailstone right here. You can actually see a core as other layers of ice form around it. Diameters usually range from 1 to 5 centimeters, and you will usually hear it compared to objects we see like golf balls, baseballs, etc. Occasionally you hear things like grapefruit or watermelon. Watermelon's a bad size. You do not want a piece of ice falling on you that's the size of a watermelon, just saying. Formation occurs in large cumulonimbus clouds. Layers of freezing rain are caught in violent up and down drafts and essentially does this. And once it's too heavy for the draft to hold, they just fall. And they can be really dangerous. Not only can they hurt you, they can hurt your car. Let's take a look at this one. We have broken windshield. You can see the dents over here in the side of the car. It's pretty crazy. And then there's rime. And rime is so cool. It's so pretty. Rime forms on cold surfaces like the freezing of super cold fog or cloud droplets. It's also really cool single player puzzle that came out, but it looks like this. It's essentially dew, but frozen. How do we measure precipitation though? Rain is the easiest to form and so the easiest to measure. We can measure them using the standard rain gauge, the tipping bucket rain gauge, or radar, like Doppler radar. So over here, we're comparing everything to the simple rain gauge. Basically, the simple rain gauge is you put a cup outside and then you put a ruler next to it and see how much water has formed. That's something you can easily do at your house. Then we get to our standard rain gauge, where you're going to have kind of like a tube with a funnel on top, and then in here is going to be more like a graduated cylinder where it'll measure how many inches of rain you get in one spot. And then we have the heated collecting funnel, or the tipping bucket gauge, where you're going to have a heated funnel to make sure nothing freezes. You're going to have a tube going down, and then on either side, you're going to have it tipped back and forth. And each compartment is able to hold 0.025 centimeters of rain. The bucket fills and tips, and each time it tips and empties the water, you have an electrical recorder actually graphing how much is being taken in by the rain gauge itself. But if you decide to use Doppler radar, it's a little bit different. This is the Doppler radar. We've all seen this before. It's kind of cool. It measures precipitation in light to heavy. It essentially uses satellites to make maps. Generally, it's known as Doppler radar because it uses the Doppler effect to produce velocity data for objects at a distance by bouncing microwave signals off of the desired target and analyzing the object's motion after the frequency of the return signal. Meteorologists use pulse Doppler technique to examine the motion of precipitation, and it's only part of the measurements. It will be used in a combination of the other measurement techniques like we have here in order to create an accurate forecast. Well, how do we measure snow? I'm sure you're all curious. You can either go outside with a ruler and stick it in and say, how much snow did we get? Or you can use the water equivalent. Generally, the ratio is 10 snow units to 1 snow unit, but this varies widely. It's actually a lot harder to measure snow because not only is it hard to measure because you could get a spot that's deeper than others, you can also get something called drifts. And what happens there is if you have a particularly bad snowstorm where there's a lot of wind, and you'll have areas where there's like no snow at all, and then you're walking, and it looks like, oh, okay, there's some snow here, and then you go thump into like 3 feet of snow. Drifts can be incredibly dangerous, especially when you have areas that dip and rise and you don't realize how deep it has gotten there. That's how people get trapped in snow. But generally, while it's snowing, you can stick a dish out and collect snow in the dish and then measure how much snow got in your dish or bucket. And that is our lecture for today. I hope you guys enjoyed it, and I'll see you guys next time.